Welcome you all to this class of Canal design, which we will be continuing today. We started on Canal design yesterday and we will be continuing with this class today again. What we were discussing on Canal design, let us just recapitulate. We started with the very fundamental concept of design of channel, and then at that point we did discuss that channel may be lined canal or it can be unlined canal. Well, now when it is lined canal, then we could see that the problem of scouring or say erosion is not there. As such, our design concept is different, or rather we try to make the channel in a most economic way. And then when we talk about unlined canal, then our problem are different. There it can be non-alluvial, the channel, I mean within the unlined category itself, there can be non-alluvial channel or the channel can be alluvial channel. Well, when it is non-alluvial channel, then again we could see that problem of erosion is not there up to a certain limit of velocity, and problem of sedimentation is of course not there, because we consider that in a non-alluvial channel the sediment carried by the water is less, and as such the sedimentation problem is not there. However, the erosion problem, as I said, that it is not there up to a certain limit, then we should maintain up to that limit of velocity. That means our design principle become such that we should decide our shape, we should design our shape of the channel, we should design our size of the channel in a way that the flow velocity does not exceed that permissible limit, that is maximum permissible velocity concept come there. And when we talk about alluvial channel, then the problem can be both scouring, that is the erosion of the bed and bank, and the problem can be of sedimentation. So, that way we just need to take care of both the cases, and it is very difficult to have analytical solution for such problem, and then generally people try to have the channel of the size so that a velocity is achieved which is referred as critical velocity. That critical velocity is that this velocity, or under this velocity the channel will neither be eroded nor there will be a deposition, so or sedimentation. So, that sort of critical velocity how we can have, that is again a very challenging task, and for that purpose generally empirical relations are used, means the equation derived on the basis of lot of observed data of such stable channel that are used, and of course some semi-empirical theory are there like tractive force method, and that are also applied. Well, and in the last class we could see that design principles are different for different type of channel, and design principle for line canal is to have the best hydraulic section, and we started with the design of rectangular channel, and then we could complete up to trapezoidal channel. Well, then again we tried to see that in trapezoidal channel the design criteria is that or the best hydraulic section is that one where the length of the side channel, length of the side slope is equal to half of the top width. That was the condition that we could derive, and using that condition again we can see that for a trapezoidal channel, when it is the best section, best hydraulic section or most economic section, it is satisfying this particular condition what we have stated, then it can be found that hydraulic radius r for that situation is equal to half of the depth, that is r is equal to y by 2, and the same condition we could see for rectangular channel as well. And in rectangular channel the condition for most efficient section we are using several terms, a most efficient section, best hydraulic section, or say most economic section. In fact, all are meaning the same thing, that is the perimeter minimum. And for rectangular section, we could see that B, that is the bed width, is equal to twice that of the depth. So, that was the condition for best hydraulic section, and of course, we have already explained what is the condition for trapezoidal section. Now, let us see what will be the condition for triangular section. We will start with that. Well, now let me take a triangular section. Well, say this is a triangular channel and this is the depth of flow, and let me just call this angle as theta, and of course, we can just give idea about this theta in terms of the side slope also, that is z is to 1. It can be written from either as theta or z is to 1, and depth of flow in triangular section is say y. Okay. Now, let us see what is the expression for area. Area is equal to half of the base into altitude. Now, what this base is basically, as we know that this top width is equal to z into y this much, and again z into y this much, because depth is 1. And so, this top width we can write as say twice z into y, twice z into y. So, our expression for area is half of the base into altitude. So, this is what the base, and altitude is y, and I mean this height is y. So, that is equal to z y square, and that will lead us to an expression for y is equal to root over a by z. Well, as now we know that our concept of making a design for most economic section is that we will try to make the perimeter minimum, that is P. If we get an expression for P, we will try to make P minimum, and in that case earlier we were doing dP dy, that is with the change of y how the P is varying, and we are trying to see that when dP dy is equal to 0, that will give us the expression for minimum value of P. Now, here we can see of course y we could change, but if we change the z, if we flatten the z, if we bring the z here, depth will automatically come down, or perimeter. So, for a given area, if we change the z value, depth will come down. If we increase the depth, if we reduce the z value, it will be coming like this, rather if we increase the z value, it will be coming like this. If we decrease the z value, it will be going like this, and then the depth of flow will be changing, and then perimeter will also be changing, weighted perimeter will also be changing. So, we can see and for design of a triangular section, what we can specify, that suppose we are asked to design a triangular section, then we can specify that well this should be the area and this should be the side slope. Once we specify the side slope, because here B we need not specify, B is not coming at all. So, B means bed width I am talking about. So, we need to specify the side slope. Well, so we can see that when P will be minimum in terms of Z also, there is a variation of P perimeter with respect to Z we can say. So, we can try to find what is dP dZ, and that way we can try to equate this to equal to 0. So, this way let us see what is the expression for P, and perimeter P let me write the expression for perimeter P, that perimeter P is equal to say this length is equal to y root over 1 plus z square. That means, this part is root over, say this length is, if it is 1 it is z root over 1 plus z square. So, this will be, this total length will be for one depth it is like that, for y it is root over say 1 plus z square, and then we will have to multiply it by y. So, this is the perimeter, and this perimeter this is only one side. So, but we have perimeter means we have both the side, this and that. So, it will be equal to 2 times of y root over 1 plus z square, and that can be written as 2 times of this y. Now, we will be expressing as root over a by z, and then we can write this as root over 1 plus z square. Well, and this can be written as, again, say if we take this z inside this root sign, then we can write it as twice root over a and root over 1 by z plus z. Well, now to have this expression in a simple form, we can square the both sides. So, squaring, what we can have, squaring this equation, squaring the above equation, what we can have, we can write this as p square is equal to, say, 4a then 1 by z plus z. Now, we can do differentiation of this equation with respect to z. So, differentiating with respect to z, what we will be getting, this is, say, twice p, then it is dp dz, and our interest is that this should become 0, is equal to 4a, and then this expression will become, this is, I am writing first dz is equal to 1, and this will become, say, minus 1 by z square, this will become minus 1 by z square. Well, if dp dz equal to 0, so dp dz equal to 0 implies, now from this expression what we can have, say this is 0 means, this left hand side is 0 means, we have that 4a 1 minus 1 by z square is equal to 0. And now, in a channel, if area is 0, there will be no flow. So, the question cannot be let area, whether area will become 0 or not. This is a product of this and that item. So, this term cannot become 0, and as such this expression must be equal to 0, and so this implies that 1 minus 1 by z square is equal to 0. This implies 1 by z square is equal to 1, and 1 by z square can be equal to 1 only when z is equal to 1, and z is equal to 1 means what we are getting indirectly, that our z is equal to 1 1. So, this z is equal to 1, that means this angle theta, the angle theta must be equal to 45 degree. So, this implies theta is equal to 45 degree. So, a triangular section will be the best section when we can have theta is equal to 45 degree, or theta 45 degree means when we talk about the total angle, then this is equal to 90 degree. So, a 90 degree channel, we can say 90 degree channel means the angle of the triangular section should be 90 degree for this is to be most efficient. And of course, in practical situation, when we propose triangular channel, then it may not be possible to provide exactly a triangular channel, and then in many a time it is given like this, and this portion is rounded up, and then we provide these things like that. But the angle, if we extend, this should be, say, 45 degree and 45 degree like that. Well, then we can go to the another type of channel, that is circular channel. Okay. In circular channel, what will happen? Say, let me draw a circular channel. Well, say this is the center, and then say flow is, we are considering that flow is up to this level. Okay, this is the water at this level, and then this length is equal to radius, means we are, suppose the radius of this circle is r. So, this is r, and in both the direction this will be r, and let me draw a normal in this direction, and this angle is theta. Well, now you can concentrate into the slide that how we can write that area is equal to, well, this entire area, our fluid is actually, or the water is in this portion. So, how we can find this area? We can find the entire area will be basically, say, like for the whole circle it is pi r square, that means twice pi is the total angle. So, half of the pi r square, and for this sector we know from our very basic geometry that it will be theta into r square, but from that theta into r square we will have to deduct this triangular portion, we will have to deduct this triangular portion, and this triangular portion, what will be the length that we can have, that this is r, okay, this is r, this is theta. So, what this length is basically, say, we can have, this is r sin theta, and what about this length, that is the height of this is r cos theta. Okay. Now, having this, we can write that flow area or sectional area of the flow, is as theta into r square minus, again we can go to half of base into altitude. So, half, and base is r sin theta is this portion. So, it will be twice r sin theta, and altitude is r cos theta. So, we are writing r cos theta. Well, this can be written as theta r square minus, say, r square by 2, and why I am writing this 2 I am not cancelling at this point, because twice sin theta cos theta we can write as sin twice theta. So, this part we are clubbing twice sin theta cos theta, sorry, I will have to leave this also, twice sin theta cos theta as sin twice theta, and then we are having this expression. Well, that can now be written as, say, r square by 2, and then we can write twice theta, this twice theta because 2 we are bringing out, minus sin twice theta. Well, this is what the expression for area. Now, expression for perimeter, here perimeter is this length, okay. So, this is what perimeter, and as we know that area perimeter, or say perimeter of the entire circle is twice pi r, that way here the perimeter of this portion will be, say, twice theta r, here our angle is this one, okay. So, perimeter P is equal to twice theta r. So, these are some of the fundamental expression that we are getting for area and perimeter for a circular section. Well, now let us again come back to the concept of best hydraulic section. Now, what we mean by best hydraulic section, again the same thing, that is minimum perimeter. So, but one point here is that for circular section, the most efficient section is considered from two different angles. Well, what that two different angle? That is, one point is that we want to maximize the discharge. Till now, in all the section or in all different type of channel shape, we were talking about the best hydraulic section is that which can carry maximum discharge. And but in case of circular section, we consider from two different aspects. One is that maximum discharge concept, one is maximum discharge, and the second is say maximum velocity, maximum velocity. Why? That is, in many cases these circular sections are used as a Hume pipe and for different practical purpose. Sometimes it become necessary, and what more important point is that discharge through this section, if we come to this part or say we are trying to find what the discharge is, then in many a time our objective is to have maximum discharge through the channel, and in many a time our objective is to have maximum velocity through the circular section, so that we can avoid siltation in the channel. And so that way, and in circular section maximum velocity and maximum discharge is not the same, is not providing us the same value. For say other section, when it is area is constant, we are having that discharge is equal to A into V, that we are getting. When area is constant, when discharge is maximized, means velocity itself is maximized, but here it is not like that. And that is why from two different angle we look into the condition, and it is found that from both the point we get little bit different expression for the efficient section. Now, from maximum discharge condition, if we go by the maximum discharge condition, say we will be getting Q is equal to area into velocity, and this means that A into 1 by N, this is our very popular expression using Manning's equation, suppose when we are using Manning's equation. But if we use Chazik's equation, say using Manning's equation, we can have this. But if we use Chazik's equation, then our expression will be different. Then it will be Q is equal to area into V, that will be A into C into root over R or A by P into SP, that we can have expression different. Well, now we have expression for this area and the perimeter in terms of theta and r. So, if we put what we need to do, okay, let us just explain. If we put the expression of area and perimeter in terms of theta and r, now for a given section r is fixed, So, if we put the expression for area and perimeter here or here, whatever, wherever it is, and then we will be having the expression for Q in terms of our theta, it will become a function of theta. And then if we go for dq d theta, we want to know that which theta will make the depth maximum. And once we get the theta, then drawing the theta we can find what can be the depth, because if we refer to this diagram, if this theta is known to us, from this theta we can find where we are actually, where this depth will be, that can be found out easily, because from here to here it is radius, and so we know that this part is r cos theta. So, depth is equal to say r minus r cos theta, that means this is the depth, So, this depth can be found out easily once we can find the theta. So, with that intention, putting value of A and P in terms of r and theta, we can get, and then equating dq d theta, well, this is dq d theta equal to 0. This will give us the value of y, this gives us value of y equal to 0.938 into d. This d is the depth of flow. Well, so y is equal to 0.938 d. But this expression we are getting when we are using Manning's equation. So, this is by using Manning's equation. But if we use Chazik's equation, then this will lead to use of Chazik's equation, that will lead to y is equal to 0.95 into the depth. So 0.95 d, it is by Chezy's equation. Well, here, so difference is not that much. Here it is 0.938, means approximately 0.94, and here it is 0.95 d. So if we want to have maximum discharge through a channel, which we will be referring as efficient section, in that case our target should be to make the depth equal to 0.95 d. And if we feel that generally a feeling may come to our mind that if a circular channel is there and if it is suppose closed channel, then we have a feeling that if the channel flow full, then the discharge will be maximum. Of course, if it flow full, the concept entirely it is changing. I mean, it is becoming a pipe flow system. We are not talking about then this open channel flow, but by open channel flow, if we make the discharge, if we make the depth equal to 0.95 d, around 9594 d, then we get maximum discharge, and we should not carry the depth beyond that limit. But then again, V can be also expressed as V is equal to this part, V is equal to this part, and so putting dV d theta equal to 0 for velocity maximum, what we can do, putting dV d theta equal to 0, if we do that, then we get that y is equal to 0.81 d, 0.81 d. So and that is important, by using both the equation. This is just slightly different, but it is around 0.8 d that we can see. Now this is important from this point, that if our target is to maximize velocity, then our depth should be kept less than, well, this d what we are drawing, what we are writing is diameter. This d is diameter of the channel. This d is diameter of the channel. This d is diameter of the channel. Not it is not the 0.938 of d. It is depth is y. So this depth is equal to 0.938 time of the diameter. Y is equal to 0.95 time of the diameter, and this depth is equal to say 0.81 time of the diameter. Okay. And we are just calculating this depth, and this is what y by y, we are writing this y, this is what. Okay. Now from that point, what we are getting, that where we should keep our y for having maximum velocity and maximum discharge, this is quite different. If we try to have maximum velocity, we will have to keep it as 0.8 time of the diameter, and if we try to maximize our discharge, then it should be 0.95 time the diameter, and this difference is quite significant. As such, this point is important. Well, with this understanding of best hydraulic section for circular channel, now we have got what will be the condition for best hydraulic section in case of trapezoidal channel, rectangular channel and triangular channel. Now we can try to design our channel using the concept of best hydraulic section for line canal, where the question of erosion is not coming. Of course, the question of deposition can come, and as such, after designing the section by best hydraulic section concept, we need to verify whether there will be sediment deposition, whether the minimum whether it is above the minimum permissible velocity, or it should not go below the minimum permissible velocity. That is important point. And suppose our lining is concrete, then also it should not exceed the value for say 3 meter per second, that should not be exceeded, otherwise there will be problem. Of course, depending on strength of the concrete, we can go for higher velocity also, but normally it should be within that range, otherwise the maximum velocity can also cause problem. So those aspects also we need to check. With this discussion on lined canal, now we can start our discussion on unlined canal, which is of course much more complex. Actual design of channel in unlined canal is much more complex than a lined channel. So, again in lined channel we can discuss it in two groups. First is that non-alluvial channel and the second is that alluvial channel. Well, first we shall start our discussion with non-alluvial channels. Well, so by what we mean by non-alluvial channel? When it is sand and silt is forming, the formation, the geological formation is suppose of sand and silt, then if we make a channel in that formation, like natural rivers are also like that, and then what is the river deposition on the side, and finally when we get that sort of landform, that we call as a alluvial landform, and that sort of channels are called alluvial channel, and non-alluvial means it is not of silt and sand. So, hard loam or say clay, muram, this sort of formation when we get, that is called non-alluvial channel. Well, and non-alluvial channel, in fact, if it is on a rock, that also we can refer as non-alluvial channel. I mean, when it is not an alluvial channel, everything we can refer as non-alluvial channel. So, this concept can goes for even rocks also. So, rock are also classified as non-alluvial channel. And as we did discuss, that silting problem is relatively less in non-alluvial channel. Why relatively less? What we mean by relatively? Because in alluvial channel we know that erosion process is quite prominent, and that is why there will be, if it is in a alluvial formation, that channel is coming from somewhere upstream, and that is also definitely passing through some alluvial formation, and then say erosion will be there on the upstream also. So, it will be carrying some sediment. But if it is a non-alluvial formation, the channel is passing from upstream, and there also erosion will not be there if it is designed properly, of course, and then as such the sediment problem will not be there. Sediment problem means flow of sediment into it should not be there, and then so sediment deposition problem should not be there. And but as I was giving one example in the previous class, that if the water is coming from a upper catchment to such channel which is otherwise non-alluvial in nature, maybe in hilly portion, but still due to rain there may be heavy erosion in the hill because of deforestation, and then all the sediment, finer sediment carried by the water will flow through this non-alluvial section, and in that case if the velocity drops below a particular limit, there may be a problem of sedimentation. So, that is why the term relatively less is coming. It can be there, but generally it is less. Well, and if we consider this to be less, then we forget about the condition of minimum permissible velocity. Then we think about only the condition of maximum permissible velocity, that is the velocity should be below a limit so that the erosion or scouring of the channel may not occur. Well, so a design is on the basis of maximum permissible velocity. Well, now when we talk about maximum permissible velocity, then we must have some idea that, well, for this particular non-alluvial formation, what can be our maximum permissible velocity? Once we know that, then it is not a difficult task for us to calculate the velocity, because using uniform flow formula, once we decide about a shape, about the size of the channel, once we decide that, then say getting the value of velocity or computing the value of velocity by using Manning's formula, say v is equal to 1 by n, then r to the power 2 by 3 s to the power half, this is very common. Once we know the slope of the channel, once we know the dimension of the channel, means r will be known to us, then velocity we can compute easily. But what information is required is that which velocity is permissible or which velocity will remain within limit for a particular material. And that we can see that this table is giving us some idea. That is, for lean clay soil or loam, this ranges from 0.38 to 1.37, and for clay it is from 0.41 to 1.67. Of course, as you can see, the range is very high. I mean, so for velocity value is concerned, the range 0.41 and 1.67 is not a very small range, and these are in meter per second. So this range is still quite large, and experience count at that point. And looking into the situation, we should know that what can be the value of this. In fact, sometimes we may have to go for experimentation also to know the exact value. But for say design of a small channel section, we may take this value and we can go by this permissible value. And when we are not sure about what will be the maximum value, then we should go for the minimum value what is being suggested as the maximum velocity, because range can be from 0.41 to 1.67 for clay, say. So if it is clay, if we do not have much idea, we should be conservative in our design and we should use then 0.41 meter per second as the value, because if we take this higher value, then we may not be sure that at lower than that also the clay surface can get eroded. Well, then for heavy clay it will range from 0.45 to 1.7. For sandy clay, when we are coming to sandy clay, then it is ranging from 0.52 to 1.83. Then muram, it is going from 0.6 to 0.9. Here range is little less and we can be more confidently we can use. For hard muram, in fact, it is given as 1.2, more confident. Then gravel is given as 1.5 meter per second. Boulder, when it is of the size boulder, that is little larger size, then this can be taken up to 1.8. Soft rock 1.8 to 2.4 meter per second, and if it is a hard rock, as I was stating earlier, that for cement concrete also you can take up to 3, and for hard rock also it is 3 meter per second or greater than 3 meter per second. It depends on what type of rock it is, and of course the chemical composition of the, or sorry, rather mineral composition of the rock matters, because when we are talking here about the strength of a rock, it is always in connection with water. So it will be in touch with water. Then how it gets weathered under the action of water, that is also important. So the mineral composition of such hard rock also we need to know, because today it may remain very hard, but with time it may undergo weathering, and then due to weathering its strength may reduce, and with time it may deteriorate. So that way these are the value. Now again, this is one point we are getting what is our maximum velocity. Then before designing, we should know one more aspect. Say a channel we want to design, then from the topography we are getting the slope, fine. Then what should be the side slope of the channel, whether it is we can go for rectangular, whether we should go for trapezoidal, that we are not knowing at this point. Well, so that is also one important aspect that we should know, and from experience and from experiment we can find out this sort of value, and these were given as suggestion, like that for clay we can go for a slope of 1:1 if it is in cutting. What we mean by cutting, that as I was explaining, say suppose natural terrain is like that, and we want to make a channel to carry something from say this point to this point, water. Now it will be difficult to go like that. So what we will do, we will make an average slope like this from here to here. We are filling up this portion, and suppose this formation is clay. So this formation is clay. Then what we will be doing, that we will fill up this portion and we will cut this portion. This portion will be say under cutting. This portion is under cutting, and this material that we will be getting by cutting, that can be filled up here to get filling portion. So this is what the filling. Now definitely when we are having a filling portion, here the clay, although it is the clay material, but will be in little loose state, although we will be trying to compact that, but still the in situ condition of clay will be definitely less, will be having less strength than the will be having more strength, in situ condition will be having more strength than the filling condition. So that way, for the portion where we are having cutting in clay, there we can go for side slope of 1:1. But if in the filling portion, we should not go for that sort of steep slope, we can go for 1.5:1. Then of course, when it is grit, then we can go for 0.5:1. And then if it is soft rock, these are we are talking about cutting soft rock, then it is 0.25:1. That way it is increasing. For hard rock, we are going for 0.125:1. And in fact, for hard rock, we can go for zero slope also. I mean, zero slope means it is vertical. 0.125 is also very small. Say it will be like this. 0.125 is also like this. Means almost vertical. Almost vertical. Say this will be. And in some case, we can even go for vertical cut. Well, so these are some information which we can use for design of this canal in non-alluvial channel. And what will be the procedure, design procedure? Say bed slope we will be getting from the topography, as I have explained. We have very small scope of manipulating that. Of course, we can do it, as I was showing here, that say this can be the slope, we can have this slope also by cutting. We can have, if we cut this portion, we can have this slope, if we fill up this portion. So slight manipulation is possible, but grossly we cannot change the slope. But still, okay, bed slope we will be knowing from the say topography. Then the side slope. This last slide will give us the side slope based on the material or based on the formation material. We will be deciding our side slope. Well, then the discharge, that we will be getting by hydrological analysis, or suppose hydrological analysis means if it is a drainage channel, we need to know how much surface runoff will be coming, and that way we can decide how much discharge will be there. But if it is an irrigation canal, then it will depend on how much water we are releasing from the main source, or what is the water requirement of the crop. Based on the water requirement of the crop, we will be releasing water, and what is the maximum requirement of the crop water, that we will have to find out. And of course, with that we need to add what will be the loss and other aspects. So that way how much maximum discharge we are allowing to flow through the channel, or we will be allowing to flow allowing through the channel, we need to know. So by some means we need to have our discharge, and that part of course we are not discussing right in this course. And then Manning's N, that is the roughness parameter. Roughness parameter we need to know from a characteristic of bed roughness and characteristic of side roughness. And in many standard book now this Manning's roughness value are available. That part we did discuss in our discussion regarding uniform flow. So, and we are not discussing it here again, but we can have this value from standard book, and many references are there. So, this will be generally known or can be obtained, as I have explained. Then after having this thing, we will have to assume a permissible velocity. So, say V is known. What should be V? Or sometimes rather than having that V, we can have, rather than having that velocity V, we can have, or we can adopt a B by Y ratio, that is width to depth ratio. And some suggestions are there, some organizations has worked, and for a particular discharge what should be the B by Y ratio, that sort of some table or graphs are available, that also we can use. Of course, this is more convenient. And then once we have this V and discharge, we can compute the area. So this area is known. Then here we can see that now we can use Manning's formula, and we can solve for the width B and depth D. because we need to know, design of channel means we need to know what is the bed width and what is the depth of the channel. So, we can now use Manning's formula and we can solve for this bed width and d, because the area is nothing but a function of b and y, and its velocity by using Manning's formula, what we can have, that 1 by n, then a by p, rather a by p to the power 2 by 3 and s b to the power half. Now, s b we already know, n we are knowing. So, v is a function of area and perimeter. Then area and perimeters are nothing but these are just expression that this area and perimeter can be expressed in terms of b and y. So, this is also a function of b and y. So, we have two equation, and we have two unknown b and y. So, these two unknown can be solved from these two expressions, and that way we can have our design dimension. Well, and then with this, now we have that understanding how we can go for design of alluvial section. So, then of course, I did not mention that if we go by the value of b by y ratio, once we have this b by y ratio, then this velocity or area, whatever we calculate, say our b by y ratio is given. So, then velocity, as it was a function of b and y, or say area that was a function of b and y. Now, what we can have, velocity, this when b and y ratio is given. So, b itself is a, suppose b by y ratio is suppose 2, then we can have b is equal to twice y. So, b itself is becoming a function of y. So, as such, this expression from this relation, what will be having, b become a function of y only, v become a function of y only, because b also is becoming a function of y. And so, from this expression we can calculate directly the depth, and once we can calculate the depth value, this is known, then again from b by y ratio we can calculate the y, this will give us y value. Well, so the size of the channel will be known, then we can calculate area and we can find out the velocity, but so this is also a procedure that we can follow once the b by y ratio is given. But only one problem is that when we are using b by y ratio, then we are getting the velocity, we are not starting from the velocity. Then once we get the velocity, we need to check whether this velocity is below the maximum permissible velocity. Otherwise, if the velocity is high, we need to adopt another b by y ratio and we should try for solving. Well, with this we can now move on to the topic of design of alluvial channel. Well, we started with design of say line canal, then we have discussed the design of non-alluvial channel, and then we can move on to the design of alluvial channel. Well, now for analyzing or for designing alluvial channel, as we are already explaining that part, that is covering, that is the erosion and deposition both can be there. So, concept of critical velocity is applied for design of alluvial channel, and then when we are using this term critical velocity, I repeat that point, that critical velocity is not the critical velocity that we were discussing when we were discussing critical flow, because we were also telling that when the flow is in critical condition, by critical condition at that time we were meaning that Froude number is 1, energy is minimum. So, that sort of conditions were there for critical depth, and the flow velocity at critical condition we referred as critical velocity. When it is higher, then we talked as supercritical. When it is lower than critical velocity, then we talked it as a subcritical velocity. But that critical velocity is quite different from this critical velocity that we adopt for design of alluvial channel. Well, this critical velocity is that velocity which will neither cause erosion nor cause deposition in the channel. Well, and to have that velocity, it is very difficult really, and then several silt theories are there, and different persons started working, different investigators started working, engineers started working on this because of their practical problem in agricultural field. Basically, it started with agricultural field. So, they found that in agricultural field, when canal were constructed with some expectation that it will be able to carry this much of discharge, then later on it was found that no, deposition is taking place in the channel, and then that is of course important. Let me just explain it little bit. When a canal was designed, suppose it was expected that this much area is there, this much area is there, flow area will be there, and sediment deposition has taken place. So, its capacity has reduced. Now its sectional area remaining is only this much because of sediment deposition. So, when the capacity reduces, then suppose we expected that this much water will be carried, but it will not be carried. This is one point. Well, that we could understand, but if scouring take place or erosion take place, then what is the problem? Well, if the canal was designed like that and scouring has taken place, so the canal has taken a shape of this one. Now, with a given discharge, earlier it was expected that the water will be flowing at this level. Now, we know that in a canal, if we expect that this is the water level, then water level, with this water level, it can move up to, say, okay, there will be a slope here, and with this water level, it is moving up to certain depth, up to certain distance. Here depth will gradually come down and it is moving up to certain distance, like that. We can show more explicitly this point, that if we just draw a slope like this and then depth is like that. So, here we have, because from a river, okay, let me draw it here. Say from a river, this depth in this side will always be higher, and then generally when we do irrigation, suppose from here we are collecting water and then we are supplying in this side. So, to what extent we can go? This canal is moving like this, and a certain extent we can go, and this side, that what is the command of that canal. A command of this canal means to what extent this canal can carry water. Now, this, if the canal size increases, then the flow depth which was earlier expected to be at this level will come down to this level, and once the flow depth come down at certain point, then the distance to which it can travel will also reduce, because the this bed resistance, size and everything changes, and then its head reduces. Total head, as we know that it is depth of flow meters, it is z plus depth of flow plus v square by twice z. Here if it is scouring is occurring, z value is coming down. Earlier suppose z value was up to this much, from here say piezometric head was up to this much level, z plus b p by w or z plus y, but now it will be only this much. So, head is coming down, and when the channel is expanding, then velocity will also drop. So, this v square by twice z, that portion is also dropping. So, total head is reducing, and when you have less head, it can flow up to lesser extent, So, the command of the canal is reducing. Command means the distance or the area that can be covered by a particular canal is called the command area of the canal. So, as it cannot carry water to far distance, so its command is reducing. And so, when we expected that, we had an expectation that we will be able to cover this much of area, but once this scouring occur, we will not be able to cover that area. So, both erosion and deposition has the problem, and because of this problem, people had to start thinking that can we have a channel section which will neither be subjected to erosion or it will not be subjected to sediment deposition, and that forced the investigator and engineers to start thinking on this particular line, and several silt theories are therefore developed, and most popular of those are, say, Kennedy's silt theory, and it was suggested by R.G. Kennedy in 1895. And most interesting point here I would like to mention that again another silt theory, or that is called Lacey's regime theory, that was proposed by Lacey in 1939 after a gap of about 40 more than 40 years. So, it was suggested, and both these theory were developed in India. These are say Kennedy was also an engineer in that field, in a field that is in a irrigation system that is called Upper Bari-Doab canal system, and that was in Punjab, of course. This now in Pakistan that place is, and now there he was engineer, and then he was experiencing this problem that I have explained, and because of this problem he then started observing that if there is if it is possible to have a stable channel, that is why his theory is always said as the theory of stable channel, and then from the entire canal system he was trying to find some channel reach which are remaining stable, or which are not changing, which are not getting affected by erosion and deposition. So, he first took those channel portion which is actually stable portion, and then he tried to observe in those stable portion at what is the secret of that. Well, and he observed the flow velocity in those channel, and then he was trying to see that this flow velocity, at this flow velocity it is remaining stable. Now, then he tried to think that this flow velocity, is it related to, of course, slope is always there, and then the slope was very say not that steep slope, these were mild slope at that portion, and then he was trying to see that whether this velocity is coming from, or whether this velocity can be related to the depth of channel or width of channel, like that he was observing, and he could later see that for that portion this velocity, achieving that velocity is depending on the depth of channel. The reason he suggested is, of course, like that erosion or scouring take place because of the, say, when the water is flowing, it has some frictional resistance with the bed, and because of that bed resistance there will be eddy formation, vertical eddy current and eddy formation, and then vertical eddy will basically lift the sediment, and then that is responsible, and for this phenomenon depth is more responsible, width is more responsible for the eddy formation on the side. So, and he, according to him, he observed that this side eddies are not creating that much of problem, or not that much of responsible for carrying the sediment, and that way he could relate, by observing these things he could plot the velocity and the depth graphically, and then he could derive a relation which was quite satisfactory for that portion. But of course, it was a very site specific study, it was for Upper Bari-Doab canal region, and then the formula he adopted became very popular, and it was known as Kennedy's formula, and it was used for design purpose. But when it was applied to some other area, then Kennedy also later could realize that no, the width of the channel has something to do with this, and this particular, for the silt characteristic of the Upper Bari-Doab canal region, only his theory is valid. For other silt characteristic, because silt will have to, the silt characteristic will have to have some important influence on the entire erosion process. So, for other region where the silt characteristic is different, his formula is not giving that stable channel as he expected. So, later on, of course, different investigators started working on that, and this formula was modified for incorporating all these possible influence of other factors, and still now also this formula is used. Of course, nowadays Less's formula is also used, and some other formula like semi empirical, or we can call the analytical approach of tractic force, is also used for design purpose in India. Well, we will be discussing all those in more detail in our next class. Thank you very much.